What if there were a mathematical cheat code that helps you find the best possible solution without checking every possibility? A tool that tells you the maximum or minimum value of something, even when you're restricted by complicated conditions. That tool exists, and it's called Lagrange multipliers. Here's how it works. When students first encounter optimization in math, finding the highest or lowest value of a function usually starts easy. You take a derivative, set it to zero, find critical points, check boundaries, and you're done. But real-world problems rarely behave so nicely. Often, you must optimize a function while being stuck inside some kind of constraint. For example, maximize profit while staying within budget, or minimize energy while obeying physical laws. You might also maximize area with a fixed perimeter or optimize machine learning functions under regularization constraints. Whenever a problem says, maximize this, but you must satisfy that, you're in the territory of constrained optimization. And this is where Lagrange multipliers shine. Lagrange multipliers give us a smart, elegant strategy for solving these problems without brute force or trial and error. The method transforms a difficult constrained optimization problem into one beautiful mathematical condition. Make the gradients of the function and the constraint line up. What problem are Lagrange multipliers solving? Imagine you're trying to find the highest point on a hill. Easy. Just keep climbing until the slope flattens. That's unconstrained optimization. But now imagine you're walking along a curved fence, and your goal is to find the highest point without leaving the fence. You can't roam freely anymore. You must stay on the constraint. So now the question becomes, where along the constraint curve does the function reach its maximum or minimum? This is key. You are no longer looking for where the slope in every direction is zero. Instead, you want the slope along the constraint to be zero. That subtle difference changes everything. The core insight behind Lagrange multipliers. To understand Lagrange multipliers intuitively, think in terms of level curves or contour lines. A function's level curves are like elevation lines on a map. Each curve represents points with equal value.
Now picture, the function you're optimizing has its own set of level curves.
The constraint is another curve on the same graph. You're sliding along the constraint curve, looking for the point where the function's level curve is as high or low as possible, while still touching the constraint curve. The magic moment happens when the level curve of the function just kisses the constraint curve. Kissing means they touch but don't cross, and their slopes match. Their gradients point in the same direction. This is the heart of the Lagrange multiplier method. At the optimal point, the gradient of your function is proportional to the gradient of the constraint. What does the Lagrange multiplier represent? The multiplier itself, usually written as lambda, measures how much the function you're optimizing would improve if the constraint were loosened by a tiny amount. In economics, it's called the shadow price, how valuable one more unit of budget would be. In physics, it's often a force or tension that keeps a system restricted. In engineering and machine learning, lambda appears in regularization methods, measuring how strongly your constraint is influencing the model. So lambda is not just a mathematical trick. It has a powerful meaning across scientific fields. Why Lagrange multipliers matter? This method is used everywhere. In physics, finding equilibrium states under conservation laws. For example, maximize entropy with fixed energy or minimize energy under length constraints. In economics, it's used for optimizing utility with a budget constraint. Machine learning regularization techniques like ridge and lasso are built on Lagrange multiplier principles. It's also vital in engineering and robotics for designing systems that must obey geometric or physical constraints. And even in chemistry and biology for molecule configurations under energy constraints. It's one of those ideas that pops up across disciplines because it captures a fundamental truth. Optimal solutions under constraints occur where two competing forces balance. A visual way to understand it. Imagine the constraint as a path you must follow. Imagine the function's gradient as an arrow showing the direction of steepest increase. At the optimal point, the direction you'd like to move to increase the function is blocked by the constraint. The gradient of the function points in the same direction as the gradient of the constraint. That alignment signals you cannot improve further without breaking a rule. It's like pushing against a wall. You can't move forward because the constraint holds you back. The power of the method. Instead of searching through every possible point, Lagrange multipliers reduce constrained optimization to a smaller, manageable system. With this technique, you find the best value under a constraint into solve where two gradients align. It's efficient, elegant, and incredibly general. Conclusion: Lagrange multipliers are more than just a math technique. They're a way of thinking about the relationship between goals and limitations.
Whenever you must optimize something under a rule, a budget, a boundary, or a physical constraint, the logic of Lagrange multipliers is at work.
They tell us the best solution happens where what you want and what you must obey are perfectly balanced. Whether you're studying physics, machine learning, economics, engineering, or pure mathematics, mastering this idea opens the door to deeper intuition and more powerful problem solving skills.